Hi, I'm Ben Harden. Let's study for Stats Exam 2. Okay, so Dr. C has told the UGTAs that we can use previous semester's Exam 2 to do some review questions on, so that's what I'm going to use. I'm going to use previous semester's Exam 2. Let's go through some questions. Okay, so this question is number 8 on the screen. You've just determined a 95% two-sided confidence interval on the ratio of two population variances, where sigma 1 is the population standard deviation of chemical process 1, and sigma 2 is the population standard deviation of chemical process 2. Your result is that your lower bound is equal to 2.32, and your upper bound is equal to 4.75. So in a two-sided test of hypothesis on the equality of these two variances, so your null hypothesis is sigma 1 squared is equal to sigma 2 squared, what would have been your conclusion? Either reject the null hypothesis, fail to reject the null hypothesis, or that you cannot draw a conclusion based on the information given. Okay, so I've broken the question up into digestible chunks. This is kind of how I think about it when I look at a question. And so what do I know right away? I've already got a 95% confidence interval. And I've got a lower bound for it and an upper bound. So I've got to compare this range to something. Well, you compare your lower bound and your upper bound to the parameter value that you're looking for. What's the parameter that I'm looking for? Well, the parameter that I'm looking for is the ratio between the two variances. My null hypothesis is that my population 1 variance equals my population 2 variance. Well, if I rewrite that null hypothesis to that ratio, then if they're equal, then that parameter value is going to be 1. So what I'm looking for here is that 1 is inside that confidence interval. I need 1 to be greater than the lower bound and 1 to be less than the upper bound. It's not. And so right away, I know that I can reject my null hypothesis. And so that's the answer to my question. Okay, so for those of you for which this isn't readily apparent, let's go ahead and break this question down, understand what it's saying, and understand what the situation is that you're in. Okay, so the question states that we've already derived a 95% confidence interval on the ratio of these two population variances. So what does that mean? And what is significant about this statement? Well, the ratio of two population variances will generate a test statistic of big S1 squared over big S2 squared that is a known probability density function. It's the F distribution. And so if in fact this parameter that we're testing for the value of 1, if it is in fact 1, then the shape of the F distribution for our parameter, which generates this parameter's characteristic test statistic, specific to the value that this guy actually takes, will have roughly this shape, where the majority of the probability density is right around the value of 1. The lower bound will be somewhere less than 1, and the upper bound will be somewhere greater than 1. But in this case, when we took a point estimate of our parameter, little s1 squared over little s2 squared, so sample variance from population 1 over sample variance from population 2, that point estimate, this value, we plugged into these equations straight out of your notes for our lower bound, and we got a result of 2.32. And we took the same value, which is, it's not specified in the question. So notice you don't even need to know what it is. But we took this same value and we plugged it in to this equation, again, straight out of your notes, and we got an upper bound on that 95% confidence interval. So 2.32 to 4.75, we got this range. Well, what do we know? We know that a lower bound on our confidence interval and our upper bound on our confidence interval, within that range, we should have 95% of the probability density. So the area under this curve should account for 95% of the area under this entire curve. And clearly that's not the case. So what does this mean? Well, it means that our parameter is generating a test statistic that has a probability density function that is an F distribution, but that F distribution has a different shape. It looks roughly like this. We don't know exactly what the shape is, but we do know that A, it's an F distribution, and B, 95% of the probability density lies between our confidence interval values. And so the majority of the area under this curve lies within this range. And the value 1 is not in this range. So we have 95% confidence that our parameter is not taking the value 1. It's taking some value between these two values. And thus, we can conclude that our parameter is probably not taking the value 1. Could be, but it's probably not with 95% confidence. And so we can reject our null hypothesis that the ratio of the two population variances is equal to 1, i.e. that the two population variances are equal. Okay, so this question is question 9 on the screen. Perform a test of hypothesis to determine if the mean time to dissolve in water is different between the two shapes. Use probability of type 1 error equal to 0.05, so alpha equals 0.05, which is the best way to express the conclusion of your test. Okay, so it gives us some options here, and the goal of any hypothesis test is to state a null hypothesis that a hypothesis test can be applied to. And so the first option that we have is to accept the alternative hypothesis. So for any hypothesis test, we're either going to reject or fail to reject the null hypothesis. That's the point of the hypothesis test. So, and further, we're never going to accept a hypothesis. A hypothesis test only suggests whether or not there is enough evidence to reject that hypothesis. So, with that in mind, I can throw out accept the alternative hypothesis or reject the alternative hypothesis. C is a valid choice, reject the null hypothesis, which would correspond to the situation where the hypothesis test results in evidence that the mean time to dissolve is different between the tablet shapes. And then option D is also a perfectly valid, is the other valid option, where we fail to reject the null hypothesis, and that corresponds to a situation where there isn't evidence. There's not evidence that the mean time to dissolve is different between the tablet shapes. And then the last option would only be relevant if, given the information, we couldn't do a hypothesis test, perhaps. Okay, so what do we need to do? Well, the question states that we need to perform a hypothesis test. In order to do that, we need to develop a null hypothesis. So that could be a little tricky, even though it's not meant to be, when you consider that there are two different valid expressions for the null hypothesis. You can either state that the null hypothesis is that the two population means are the same, or you could state that the null hypothesis is that the population means are different. Note that in each situation, the statements for the null hypothesis and the alternative hypothesis are just reversed. So what does that mean? Well, it means that you would perform the hypothesis test and then you would just interpret your result appropriately, either rejecting or failing to reject the null hypothesis in each case appropriately. So does it matter for this question? Well, it does. And it does because option C constrains rejecting the null hypothesis to be the situation where there is evidence that the mean time to dissolve is different between the tablet shapes. Or in other words, it constrains the null hypothesis to be the statement that the population means are the same. Now, in order to do a hypothesis or perform a hypothesis test, we need to test a population parameter against a value. And so the way we're going to do that is we're going to rewrite the null hypothesis to state that the difference between the two population means is equal to 0. Okay, so we've developed our null hypothesis. It states that the two population means are equal, or in other words, that the difference between the means of the two populations is equal to 0. So what tool are we going to use to assess our null hypothesis? Well, in chapter 10, we've been given 3 tools that are related to our null hypothesis. The first is a test of hypothesis on the difference between two population means with population variances known. The second tool is a test of hypothesis on the difference between two population means with the population variances unknown but likely equal. And the third tool is a test of hypothesis on the difference between two population means with the population variances unknown but likely unequal. In the problem, we've been given 2 sample sets. We've been given a set of sample data for the oval-shaped pill, and we've been given a set of sample data for the round-shaped pill. And we've also been told to use a probability of type 1 error of 5%. That's it. So right off the bat, I don't have any population variances. So I'm going to do a test of hypothesis on the difference between two population means with the population variances unknown. One of those 2 tests. So how do I determine which one to use? Well, I need to figure out whether or not the population variances are likely equal or unequal. Okay, I need to determine whether or not our population variances are likely equal or not. So we're going to do that with a hypothesis test on the ratio of two population variances. Now, you can do this in 2 ways. In the question label number 9, the lower bound and upper bound for your 95% confidence interval was not derived. It didn't need to be derived, it was just given to you. So you could derive those here with the information that you're given. The question gives you the number of samples that have been taken from each population, and you have an F table. And the equations, or the procedure for deriving your lower bound and your upper bound are in the notes. And you will have had homework questions that helped you through verifying that you knew how to do that. And so it's absolutely perfectly reasonable for you to derive your lower bound, your upper bound, and make sure that the value 1 lies within that interval. But for me, I like to give myself the best opportunity to make as few mistakes as possible. And I find that the best way to do that is to minimize the number of steps and calculations, specifically calculations, that I need to do in order to solve any problem, because I am prone to transcription errors, and I think that most humans probably are. So I'm going to do this with the calculator. This is one of the more involved questions that you're going to encounter. It involves 2 hypothesis tests back to back. I remember this being pretty stressful. I think this is one of the questions I got wrong, but this is a gimme question. This is easy points. So try it at home. Do it both ways. But I recommend using the calculator and just pounding this out, and you'll see how quick this is. So let's do the test of hypothesis on the ratio of 2 population variances. Okay, so I have stated my null hypothesis, which is equivalent to my 2 population variances are equal. But the other way to say that is the ratio of the 2 population variances is equal to 1. And then these are almost literally my calculator button presses into the calculator. So I'm using a TI-83 Plus. The way that you do this with your calculator is going to vary just a little bit, but the way that I've written it, it's pretty agnostic. Suffice to say that if you haven't already, what you want to do is you want to Google how to use the 2-sample f-test for your calculator, and then later the 2-sample t-test for your calculator. So we're going to use the 2-sample f-test right now. So what I'm going to type into my calculator is literally, so I'm going to enter each one of my sample sets into lists. The first population 1 sample set is going to go into list 1, and population 2 sample set is going to go into list 2. And the way that I do that is I do open curly brace, and then each value of my sample separated by a comma, and then I'm going to type in a closed curly brace. This is the calculator store function, which I'm sure you're familiar with, and then this button, or this reference right here, is literally the button's second and the button 1. And on my calculator, that's a reference to list 1. And so with those button presses, list 1's populated. I'm going to do the same thing for list 2. I just like to pound these in to the computer face right away. When I press enter, I get the values back, and I know it's in there, and I can just move on with my life instead of going into that list editor interface. Some people like that list editor interface. You know, you can see the first 10 entries of 4 lists wide, and that's that's super awesome. If that's what you dig, then do that. But this is the most reliable way and quickest way for me that I can validate that I haven't made a mistake. So then I'm going to go into stats, and I'm going to find my 2-sample f-test. I'm going to make sure that the data field is highlighted, and I'm going to make sure that list 1 has been entered, which I think it will be by default. I don't know. You should look. But anyway, I'm going to make sure list 1 is entered for the list 1 field, and I'm going to make sure that the value list 2 is entered for the list 2 field. I'm going to make sure that the value 1 is entered for both fields, frequency 1 and frequency 2, which I have no idea what those mean, and neither do you. And you don't need to either. And then at the bottom, I think this actually looks like this on my calculator. There's 3 fields, and this is the first field that tells the calculator that we want to do a 2-sided hypothesis test. Okay, and so at the very, very bottom of that 2-sample f-test function interface, there's a calculate and a draw, right? And I always hit calculate. I don't ever use the draw function because sometimes when it turns out that this probability is very low, the draw function fails. So I'm going to hit calculate, and I get I get a whole bunch of data. The data that we care about right away is the p-value. I need to compare my p-value to my probability of type 1 error. Specifically, my value for alpha over 2. The value that we're interested for alpha over 2 is 0.025. And so the p-value that I get is 2 point something times 10 to the negative fifth, which is much less than my value of alpha over 2, which is 0.025. And so based on that, I can reject my null hypothesis, and I can conclude that probably my population variances are not equal. So I should add that if the p-value that I got had been greater than 1 minus our alpha over 2, so if the p-value that we got was greater than 0.975, I would have also, we would have also rejected our null hypothesis. So I should also add that during this hypothesis test, I chose my rejection criteria. I chose the probability of type 1 error for which I would reject the null hypothesis. So I picked 5%. I could have picked 1%. So a value of alpha of 0.01 or alpha over 2 of 0.005. And if I had done that, I would still reject the null hypothesis because this value that I got for the p-value is 0.00002, which is still much less than 0.005. Okay, so we've determined that our two population variances are likely not equal. And so what does this mean going forward? Well, for a hypothesis test on the difference between two population means with the population variances unknown, we have two cases. And each one of those cases corresponds to one of the tools that we have available to use. So case one was that the population variances are equal. We've determined that we're not in that case. We're in case two. Okay, so now we are going to go and find our two sample t-test, and we're going to make sure that list one and list two are, those values are entered for our list one and list two fields respectively, just like in the two sample F test. And for the frequency one and frequency two fields, we're going to make sure that the value one is entered there. And at the bottom, we're going to choose this option, which it has mu1 not equal to mu2, which tells the calculator we're going to do a two-sided hypothesis test. And then we're going to choose, for the field that says pooled, we're going to choose no. And again, I don't know what that's like on your calculator, but whatever option corresponds to not pooled. Okay, so you enter that and it gives us back, again, a whole bunch of data. Okay, so in the data return, what do we care about? Well, we care about the p-value. And we got a p-value of 0.67, which is much greater than our threshold of 0.05, for which the question stated we needed to use for the probability of type 1 error. And so from that, simply from that data right there, we can conclude that we are going to fail to reject our null hypothesis, that the difference between the means of our two populations is likely 0, and thus that the means of our two populations is likely equal. Okay, so this question 10 is a follow-up to question 9. It says, how many degrees of freedom will your test statistic in the test of hypothesis to determine if the mean time to dissolve in water is different between the two shapes? And so out of the notes and out of the book, If we're in a case 1 situation, then the degrees of freedom is just the number of samples from population 1 plus the number of samples from population 2 minus 2. But if you're in a case 2 situation, then it's a much more complicated equation. And so it's this guy right here. And it's why there's a real big advantage to using your calculator, because in that 2-sample t-test, it just spits it out for you. I've got 3.008. And if you notice, that is the option B and the correct option for this question, or the correct answer for this question. Okay, so real quick, I just want to summarize big picture. I want to generalize this test of hypothesis between two population means. Okay, so if they give you the population's variances, then you're going to do a 2-sample z-test. And that's just another function, right? And you're going to give it the appropriate input data. It's either going to be the actual sample values, right? And you're going to enter it as, list 1 and list 2, or you're going to highlight the stat, button or field, and it's going to ask for the sample standard deviations or the sample variances. I can't remember which, but it's one of those two, right? And so they'll either have to give that to you, or you'll have to be able to derive that somehow. But I think they'll either give you that. They'll probably give you that. So if they don't give you the population variances, then you're going to have to do a test of hypothesis in order to determine whether or not the population variances that you don't know are likely or unlikely to be equal. And so you're going to do this procedure here. You're going to do a test of hypothesis on the ratio of two population variances, right? You're going to use this 2-sample f-test, and if you're given the actual sample values, you're going to enter them in the list. If you're given the sample standard deviations, you're going to highlight the stat button here, and you're going to enter those instead. And then it's going to give you a p-value, and you're going to compare that to your probability of type 1 error. And then from that, you're going to determine whether or not you're in case 1 or case 2. And again, either you're going to have those sample values, and you're going to punch those sample values into your lists, which they'll already be in there because you had to do this hypothesis test, or you're going to, again, select the stat field, and you're going to enter the given sample standard deviations or the sample variances, whichever it be. Chances are, if your calculator requires the sample standard deviation, the question is going to give you the sample variance, and you're going to have to, do a quick calculation. Either way, this question shouldn't stress you out. It's an easy 3 points. Just practice this a couple of times, and for the different configurations that you could be in, you're going to be real comfortable if you just do this a couple of times. Okay, so this next question is a fill in the blank, labeled 11. The value of 1 minus alpha in a hypothesis test is the probability of blank, identifying a true null hypothesis. And so we're given the options mistakenly, deliberately, incorrectly, and correctly, or none of the answers. All right, so let's take a look at this. Okay, so we're looking to answer the question, what is the interpretation of the value 1 minus alpha? So straight from the notes, I've written up this rubric that's been given to you, and I think that you had to fill in. And from here, we can see that we're looking for 1 minus alpha. 1 minus alpha is the probability that you do not commit a type 1 error. And so, in other words, it's the probability that you find yourself in the situation where you failed to reject H naught when H naught is true. So, what's the right answer according to the question? Well, 1 minus alpha is the probability of correctly identifying a true null hypothesis. Okay, so this question, labeled number 12, let's go over it. It says the mean water temperature downstream from a discharge pipe at a power plant cooling tower is specified to be 99 degrees Fahrenheit. Past experience shows that the population standard deviation is 2 degrees Fahrenheit. The water temperature is taken on 9 random days, and the sample mean is computed to be 97 degrees Fahrenheit. If the true population mean water temperature is 101 degrees Fahrenheit, what is the probability of type 2 error using a probability of type 1 error of 1%, or alpha equal to 0.01. All right, let's jump into it. So we have some population, and we're interested in its population parameter, the mean. And we're going to do a hypothesis test on that mean and test it against the value 99 degrees Fahrenheit. So we know that sampling of this population will generate a test statistic that has a normal distribution. And there will be values for that test statistic that correspond to a confidence interval of the probability of type 1 error that we're interested in. And in this case, that's 1%, or alpha equal 0.01. So I'm going to go ahead and grab those values. And so I've made these calculations already. The value of my test statistic corresponding to 1 minus alpha over 2 is the value returned by this function, so inverse norm, and you give it the value of 1 minus alpha over 2. For the value of the population parameter we're testing against, which is 99 degrees Fahrenheit, and the standard error, which is the population standard deviation, which we're given, divided by the root of the number of samples taken. So this is going to be 2/3. So we get this value, 100, it's about 100.717. And so I can calculate what the value is for my test statistic that corresponds to alpha over 2. Okay. So if in fact the true population mean is 99 degrees Fahrenheit, we're going to have this confidence interval that corresponds to this probability density in between these values. However, the question asks, what is the probability of us committing a type 2 error if the true population mean is 101 degrees Fahrenheit? And so let's remember that the probability of type 2 error corresponds to the probability of the situation occurring that we fail to reject, or we believe the null hypothesis for an untrue value that we're testing against. So, what's this look like? So, we have some probability that corresponds to a 95% confidence interval for this incorrect value. But if in fact we were testing against 101 degrees Fahrenheit, so we would get a probability distribution that corresponds to this parameter value that looks something roughly like this. It's just another normal distribution. Well, that's not very normal, is it? Well, that's... And so if our sample mean ends up lying somewhere between these values, then we're going to have a probability of believing that the value we're testing against in our hypothesis test is correct, when in reality it's not. And the overlap here of this probability density is the probability that this is going to occur. This is the probability of type 2 error. So, how do we calculate this? Well, it's just the norm CDF function between these values, so 97.283 and 100.717. And so the true parameter value is 101. And then the standard error, which we know, which is just 2/3. And that's going to result in a probability of about 33.6%. Which means that equals 0.336. Okay, so the last question that I'm going to review is, it's the one labeled 13. For a fixed value of the standard deviation and a fixed sample size, the length of a confidence interval on the population mean will get smaller as the level of confidence increases from 95% to 99%. So this is a true or false question. So let's take a look. The question asks for a fixed number of samples, and thus for a fixed sample standard deviation if the length of a confidence interval gets smaller as the level of confidence increases. So I've drawn a diagram, and the annotation in yellow corresponds to the length of the confidence interval for a 95% confidence interval. And the length here in red corresponds to the length of the confidence interval for 99% confidence interval. So you can clearly see that as the level of confidence increases, so does the length of the confidence interval. And so the answer to the question is false. So just a couple of recommendations. So for the tests in IE 380, I found that reading over the entire test, just taking a minute or two to read over the entire test as soon as you open it and not trying to attack anything right away, really kind of helps your mind kind of organize all the information that it needs to gather and also identify the questions that you're very confident that you can nail. So the way to kind of think about the test is you're trying to grab all the points that you know you can grab and then attack the points that you have a reasonable probability of getting. And then with the time left, you get those Hail Marys. And so I find that reading through the test first and seeing the spread kind of gives my brain a head start and calms some anxiety. And then also something that I find super useful and just over and over and over again. If you read a question and it's not laying down and your head's starting to spin a little bit, skip it. Just skip it. Period. Go on to the next one. Go find the next one that your mind wants to tackle or has the next highest amount of confidence to tackle. Nail it. Then go back through. You don't have to take the questions in order. Although I will say on Dr. Chatton's tests, a lot of times the subsequent question is fed into by the previous question. So the previous question will kind of refresh your memory on certain concepts or utilizing certain functions in the calculator, and then the next question will kind of build on it. And you know, that kind of chain of questions does occur, but for the most part, attack the question. Let your brain decide what the next question you want to attack is, not the question number. Yeah, and good luck.